Hello. This video is going to pick up with a further discussion of how the surface integral is used to calculate surface area. In our previous discussions, we calculated a surface area of surfaces whose equations were given as functions of x and y. And in that case, and in the case we're getting ready to look at, the surface integral for surface area is what you see right here on the screen. It's just the integral of 1 ds. So the differential ds points to the fact that we're integrating over some other surface than the xy plane. In the case where our surface can be expressed as a function of x and y, ds ends up being the square root of the partial derivative of z with respect to x squared plus the partial derivative of z with respect to y squared plus 1. But in many cases, the surfaces cannot be expressed as functions of x and y, and they may instead be given to us as smooth parameterizations. So that's where we're going to start our discussion today. So our surface S is parameterized by a vector function r of two parameters u and v for u and v elements of some domain D. So in that case, the differential ds is equal to the magnitude of the cross product of two partial derivative vectors, dA. So these partial derivative vectors are one with respect to u and one with respect to v. Both of these are themselves vector functions. And r of u v is a vector function of three components, where each component is parameterized by u and v. So r sub u of uv simply means that we need to take the partial derivative of the x component with respect to u. Y sub u is then the partial derivative of the y component with respect to u, and z sub u is the partial derivative of the z component with respect to u. And r sub v is defined similarly. So let's look at a specific example where we want to find the surface area. In this case, S is the portion of the surface parameterized by r of uv, given there, whose pre-image is the unit square 0, 1 by 0, 1. So this idea of the pre-image is that in the uv plane, we only care about the portion of the surface that is above that square, 0, 1, 0, 1. This surface without bounds on u and v would go infinitely in all different directions, but we're bounding it to the portion that's above 0, 1 by 0, 1. So to evaluate the surface integral to calculate surface area, we need to first calculate ds. And ds, as we saw in the last slide, is equal to the magnitude of the cross product of the two partial derivative vectors. So our first step should be to find the two partial derivative vectors. I need to find r sub u and r sub v. In this case, both partial derivative vectors are very easily found because the original parameterization is nothing but linear components. So both of our partial derivative vectors end up having constant values for each component, and so we get constant vectors as the partial derivative vectors. Once we have the partial derivative vectors, the next step is to calculate their cross product and then to find the magnitude of that cross product. We've done lots of examples of calculating cross products, so I'm going to leave that calculation to you to check out on your own. I got 2, negative 2, 4, and then I take the magnitude of that vector to get to square root 6. And the only thing left to do now is to write out the actual surface integral. So the integral of 1 ds, this is what represents our surface area, is equal to the double integral over our domain D of the magnitude of the cross product of the partial derivative vectors, dA. We found the magnitude of the cross product of the partial derivative vectors was 2 root 6, and then our domain D is a square from 0 to 1 and 0 to 1. So we integrate du dv, or you could alternatively integrate dv du. In either case, doesn't matter, we get 2 root 6 as the surface area of the surface above 0, 1 and 0, 1. Now we want to look at a further extension of the surface integral. What if we want to integrate some function over a smooth surface, a function other than 1, but still being a scalar function? Notice this is f of x, y, z. So it's not a vector function, it's a scalar function. So we have the integral of f of x, y, z ds. So if our surface S is still parameterized by some vector function r of u and v, then we can interpret the surface integral in this way. So we would need to replace the values of x, y, and z with their parameterization equivalents, and we'd need to add in that extra factor for ds of the magnitude of the cross product of r sub u and r sub v. Now, something that's a little more difficult to understand in this case is what is it geometrically that we're actually doing when we do a surface integral of a function. So one potential explanation is that we're calculating mass. So if you think of f as a density function, we'll use rho. So instead of f, we have rho of x, y, z. Then what you could interpret the value of this integral to be is the mass of a non-planar object, where rho is the density function. So rather than the mass of something lying in the xy plane, we can now find the mass of something lying anywhere in space, as long as it is a smooth surface. I want to demonstrate an example of this. Let me move the video down just a little. There you go. So I want to integrate over the surface S. In this case, S is going to be the portion of the unit sphere in the first octant, and we're going to integrate this function over the surface. F of x, y, z equals e to the z. So as we spoke about on the last slide, one way to interpret this is we're finding the mass of the unit sphere in the first octant if its density is given by the function e to the z. So before we can proceed, we need a parameterization for the unit sphere in the first octant. A rectangular equation for the unit sphere centered at 0 would be x squared plus y squared plus z squared equals 1 squared, which is 1. So any parameterization must satisfy that equation, x squared plus y squared plus z squared equals 1. The parameterization I'm going to posit is r of theta phi equal to the vector function that you see here. And this is a valid parameterization, because if you plug in the x component, the y component, the z component, and square them and simplify, you will see that you do come out to a value of 1. Now, I will grant that it's not exactly obvious to come up with this parameterization, but this is a good one to know and to use in the future. And this parameterization is for theta values between 0 and 2 pi, and for phi values from 0 to pi. That gives you the entire unit sphere. Of course, we only care about the portion of it in the first octant, so we're going to bound theta and phi differently when we go to calculate the surface integral. But for now, the parameterization would work over those entire large intervals. Once we have the parameterization for the unit sphere, we can then calculate the partial derivative vector functions. Since I used theta and phi for spherical coordinates instead of u and v, we're going to find r sub theta and r sub phi. Again, those just indicate partial derivative functions. So we're going to find the partial derivative of this component with respect to theta, the partial of this component with respect to theta, and the partial of this component with respect to theta, and then we're going to do it again with respect to phi. And so if we do that, you should get these two partial derivative vector functions. And I leave it to you to verify that those are the exact answers. Once we have the partial derivative vector functions, our next step is to calculate their cross product and then to find the magnitude. So without me writing all the steps down for you, the vector you see here is the cross product of r sub theta and r sub phi. And then when you find the magnitude, interestingly enough, everything goes away until you're left with the square root of sine squared phi. And the square root of sine squared phi is the absolute value of sine phi. But since phi is bounded between 0 and pi, then we can just write the absolute value of sine phi is the same thing as sine phi. The last step is to actually set up the surface integral. So we're going to change from the integral of s of f of x, y, z ds into a specific double integral. So in general, this is what we're doing. And then here is the specifics to our particular problem. So we switch to a double integral, and we're going to now integrate with respect to theta and phi. So the integrand, rather than being e to the z, becomes e to the cosine phi, because that is what z was equal to in our parameterization of the unit sphere. Then we added in the extra factor of sine phi, which came from the magnitude of the cross product of the two partial derivative vectors. And lastly, we see the bounds are 0 to pi over 2 and 0 to pi over 2 for both theta and phi. That's because we're working in the first octant only. Remember, theta measures rotation in the xy plane. So if we want the first octant, we only want the first quadrant in the xy plane. So that's, well, for theta values between 0 to pi over 2. And then phi measures rotation down from the positive z-axis. So we only want to go down to the xy plane, so we only want to go down pi over 2 units. So that's why it is also 0 to pi over 2. Integrating with respect to theta is very easy on this one to begin with, because there are no thetas. So this is a constant with respect to theta, and we get this integral. Lastly, we have to integrate with respect to phi, and that's a simple u substitution where you allow u to be cosine phi, and du is negative sine phi. So insert a negative inside the integrand and one on the outside of the integrand. We get this expression, plug in our values, we get pi over 2 times e minus 1. So if you're looking to interpret that, like what does that actually mean? As I said before, one way to think of this is that pi over 2 times e minus 1 is the mass of the unit sphere in the first octant if its density were given by this function, e to the z. And that's going to be the end of this video. And next time we will discuss how surface integrals can be used to calculate flux.